The video 17-1. The temperature, the heat and enthalpy, the specific heat, the heat reaction in thermochemical equations, and the energy diagram. Okay, so chapter 17, looking at energy in the first half, and the second half of the chapter, second test, will be on reaction kinetics. Okay, so first thing, thermochemistry. Okay, as the name implies, the name thermal. Okay, study of the transfer of heat and that accompanies chemical reactions and physical changes. Okay, so first of all, let's go over some definitions. This first one, temperature does not measure the amount of heat that something has. Okay, remember, it's a measure of the average kinetic energy of the particles in a sample of matter. Okay, why doesn't temperature measure heat? Well, do objects at the same temperature contain the same amount of heat? So you can have a whole bunch of different objects, or they could even be the same. But remember, if they have different masses, they can have different amounts of heat, even though they're at the same temperature. Okay, so how can we measure heat? Okay, well, we actually measure something called enthalpy. Okay, this is basically the heat content of a system, okay, and at constant pressure. So as something gains heat energy, its enthalpy increases, okay? But that does not necessarily mean that its temperature is hotter than something else. Okay? Now, one problem with enthalpy, it cannot be directly measured, okay? You cannot stick a thermometer into an object and say, oh, I can figure out the enthalpy of it, okay? Because remember, things with different amounts of enthalpy can have the exact same temperature. Okay? So, what is this thing that we call Q then, that we call heat? And by the way, the symbol for heat is Q. Okay? Heat is a form of energy that will be transferred between samples with different temperatures. Okay? And heat will always transfer from a higher temperature to a lower temperature. Okay? Be careful of this because you can get enthalpy to transfer for something with a low enthalpy to a higher enthalpy. If object 1, object 2, heat can transfer from low enthalpy to high enthalpy. Okay, why? Simple. T1 can be hotter than T2. Okay, so you can have a really small object that's hot. It doesn't have as much enthalpy as a really hot, large object that has a lot of enthalpy in it, a lot of heat energy, but it's colder. Okay, so if T1 is greater than T2, the heat will transfer from object 1 to object 2. Okay, even though this thing can have less enthalpy than that one. Okay, now, units for enthalpy, it's energy. So simply we use joules. Okay, sometimes we will use the term calories also. Okay, now, calories, this is the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is your definition of a calorie. Okay, now watch out for food calories. Okay, food calories are a kilocalorie. It's 1,000 of these calories. Okay, and that's going to be equal to 4.18 joules. Okay, remember 1 calorie is equal to 4.18 joules. There's your equality. If you got 1,000 of them, you need 1,000 of those, and the equality will still work. Okay, now how do we measure heat? Well, we can't measure the heat content, the enthalpy, directly. Okay, but we can measure changes in heat content. In other words, if heat transfers into an object or out of an object, okay, the amount of heat transfer positive, okay, means the system is gaining, and the surroundings that lost the energy has to be a negative sign. It's losing it. Okay, so you have to define what we're talking about. If this is our object right here, okay, if heat transfers into it from the surroundings, basically the surroundings is going to lose enthalpy and the system will gain enthalpy. Okay, so delta H will increase and delta H of the surroundings will decrease. Okay, positive means heat is entering the system or being absorbed by the system. Okay, now, if we have two different objects with the same mass and they absorb the same quantity of heat, okay, do they end up at the same temperature? Okay. Sometimes yes, sometimes no. Okay. Now, why is it that both two objects, object 1 and object 2, could both absorb the exact same amount of heat, but T1 and T2, T final and T final, will not be the same? Okay, simple. There is something called the specific heat capacity of an object. Okay, and this is the amount of energy required to raise the temperature of 1 gram of that substance by 1 degree Celsius, okay, or by 1 degree Kelvin, because the increments are exactly the same. Okay, now, if something has a large specific heat, it's going to heat up slower. Okay, why? If the object has a large specific heat, that means it requires more energy for it to heat up. Okay, so more heat has to go in before the temperature will increase by 1 degree Celsius or Kelvin. Okay, and the units are joules over grams times Kelvin. Okay, now, if we know the specific heat of a substance and the change in temperature that it underwent, okay, so this is basically delta T, we can figure out how much heat was transferred into the object or out of the object. Okay, and we use this formula right here. Q, the heat transfer, is equal to mass of the object times C, specific heat capacity, times delta T. Okay, and this will be equal to delta H for the object. Okay, the change in enthalpy for that object. Okay, and how do you figure out C? Whoops. These are based on values given in the table, the specific heat capacity values. Okay, so here's a little problem. How much heat is needed to raise the temperature of 35 grams of water from 20 degrees Celsius to 35 degrees Celsius? Okay, so we're looking for Q. Okay, and it's equal to M times C times delta T. Okay, so the mass is the mass of the object, which is 35.000 grams. Okay, delta T, make sure you calculate it correctly, final minus the initial, 35.00 minus 25, or whoops, 20.00. So that's going to give you 15.00 degrees Celsius. Okay, and what's C? Well, C for water. You can look it up, or we can figure it out. Okay, remember, specific heat capacity. How much heat is needed to raise the temperature of 1 gram of water by 1 degree Celsius? Okay, if you remember your definition, this was a calorie. Okay, so for water, I want to do it in joules though. 1 calorie is 4.18 joules. Okay, units are joules over grams times degrees Celsius or Kelvin. Okay, so plug our numbers in. Q is equal to M, 35.00 grams, times C, 4.18 joules over grams times Kelvin, and delta T. Notice the units here are in degrees C. But if I do a change in temperature, if delta T is equal to 15.00 degrees Celsius, it's also equal to 15.00 Kelvin. Okay, why? Because the change on the Celsius scale is the exact same as it is on the Kelvin scale. So a change of 15 degrees Celsius is also equal to 15.00 Kelvin. Okay, units cancel out, grams cancel out, okay, and you can complete the calculation. Okay, heat of reaction. Just about all chemical reactions will show a change in enthalpy between the reactants and the products. Don't forget, enthalpy is the internal energy. Okay, so if the reactants end up gaining energy, okay, then this is an endothermic reaction. Okay, and the products will end up with more enthalpy than the reactants. That doesn't mean they will be hotter. It just means that they have more, the enthalpy of the products is greater. The total internal energy is greater than that of the reactants. Okay, delta H will be a positive value for this reaction. Okay, if the reactants lose heat energy in the reaction, then it's an exothermic reaction. Okay, products have less enthalpy than the reactants. So the reactants had more energy, the products end up with less energy. Okay, and delta H will be negative for this kind of reaction. Okay, remember, we don't know what the enthalpy is of the reactants or products, only the change. Okay, so we can always figure out delta H. The problem is we don't know the delta H of the products or the delta H of the reactants. Okay, but this can be measured. The individual ones cannot be measured. Okay, now once you know delta H for the reaction, this can be measured, okay, through simple means. Remember, delta H is simply equal to Q, the amount of heat that was either transferred in or transferred out of the reaction. Okay, once you know delta H, you can write it in the reaction. Okay, if delta H is positive, then it's a reactant. If delta H is negative, then you write it as a product. Okay, so an example right here. For this reaction, 2 moles of hydrogen plus 1 mole of oxygen gives you 2 moles of H2O gas. It also produces it produces 483.6 kilojoules. Okay. The delta H for this reaction was negative 483.6 kilojoules. Why? Because heat is a product. The negative sign means it's exothermic. Okay. This is known as a thermochemical equation. What does thermochemical mean? Simple. You put the delta H into the equation. Okay. If it was a positive value, you put it on the reactant side. Okay. Now, once you put this in to the equation, the coefficients can now only stand for moles. Okay. So, energy diagrams. If the reactants have more energy than the products, okay, then delta H is negative. Okay. Heat had to be given off. That means this is an exothermic reaction. Okay. And if the products end up with more energy than the reactants, that means the reactants had to gain energy, so delta H for this reaction, the change in enthalpy was positive, and this would be an endothermic reaction. Okay, here's your review question.